Assalamu alaikum. How you doing, guys? Today I'm going to be showing you some examples of designing of reinforced concrete beams. But before I do, I would like to talk about the four major categories in design. So let's start the first one. The first one is usually we have what I call a fresh design. You have no clue. Then by that you will have B, H, and the area of steel, all are unknowns. Okay, all three of them. So the way to approach that is you probably will have some ratio between B and H, like we showed you. Let's say D is equal to 2.5 B. So there's a relation between B and D, obviously, from which you can get H. And then there is still usually we assume some reinforcement ratio. Usually it's rho max or some ratio off of that, maybe 0.6 rho max, or you just can use rho max if you wish. And I will show that in the following examples. Actually, that's the example that I'm going to start with. The second category might fall under that, well, I know my H. Okay, when I say H, you already know D. Okay, so that's synonymous with that. So in the cases where I know H is when I want to design what I call a hidden beam, and the height of the beam is the same height of the slab, and you usually know what the height of the slab is, and from that you will know the height. So this would be known, but then the width and area of steel are unknown. The third category might be where I know my B, and that is if you would like to design your beam to be flush with the column. So the width of the beam is the same width of the column. And at that point, H and the area of steel are both unknown. The last one is where I know both my B and my H. And that could be, just like we said, maybe hidden beam flush with the column, but the most obvious case for that is when we have continuous beams, and in that case only the only unknown would be my area of steel. So let's say if I have a continuous beam like that, then my moment diagram would look something like this. Okay, here is my positive moment, negative moment, positive moment. So if I have, let's say, M1 here, M2, and M3, and let's assume that my M1 is larger than M2 and is larger than M3. Then I will base all my design on M1, the largest, and that would be somewhat like case 1. Okay, so I'm designing my beam on the maximum of the maximums, let's say. So again, this is my positive moment, negative moment, positive. All right. So once I do that and determine BH and area of steel for that section right here, now the beam obviously will have the same cross section all over. So when I go and try design for M2, then that case would be this right there, because I already found my B and H from the maximum moment of the entire beam, and then all I have to do is just find the area of steel here, and then the area of steel in this region right here. And that's the region where I told you sometimes the cross section might be big enough where I might not need any steel reinforcement, and where this is the case where I would usually use my minimum. Okay, assuming that M3 is a very small value. Okay, so these kind of are the categories that you're going to jump in between to do your design. So having that said, let's start with the first example in this series. So for the beam shown below, he needs to find a BH in the area of steel. Now I'm assuming that I'm having a compressive strength for concrete of 22 megapascals. Yield steel is 420 megapascals. I'm using Phi 8 stirrups. I'm assuming D to be 2.5 B. Here I'm using my rho to be the same as rho max, and I'm going to use a 40 millimeter cover. Now the length of the beam center to center here is 4.5 meters. The dead load is 25 kilonewton per meter, and the live load is 40 kilonewton per meter. From that, I can calculate the ultimate load, and that's simply 1.2 times the 25, the dead load, plus 1.6 times the live load of 40, and that will give me an ultimate load of 94 kilonewtons per meter. From that, I can calculate my ultimate moment, and since it is a simple beam, then the ultimate moment would be WL square over 8, and that will give me a maximum moment, ultimate moment of 237.94 kilonewton meters. So, since he wants me to use rho max, I'm going to find out what rho max is. So rho max is 0.85 times 0.85, because my f prime c is less than 28, times the f prime c 22 divided by fy 420. And this is epsilon ultimate for concrete, and this is again the crushing epsilon ultimate, and this is here for the 0.003 plus epsilon ty, which in this case is going to be 0.005. From that, I'm finding my rho max to be 0.014192. Now we know that the m ultimate is going to equal to phi mn. So the ultimate moment, 237.94 times 10 to the 6. And please use 10 to the 6 because now you're converting from kilonewton meters to newton millimeters. Okay? If you don't do that, you're going to get some very weird numbers. Right? So now this is going to be equal to phi, which is my 0.9. This is my rho, which I said I'm going to use rho max. If it's 0.6 rho max, then you just multiply by 0.6 if you choose to, but we didn't for this example. Times Fy, these are the two unknowns, BD square, 1 minus 0.59 times, again, this is my rho max, Fy, F prime C. From that, I'm able to find that my BD square is equal to 52.75 times 10 to the 6 millimeter cube. Again, emphasize the millimeters, all right? So now I'm going to use the fact that D is equal to 2.5 B. Then from that I will have P cubed is equal to 52.79 times 10 to the 6 divided by 2.5 squared. So from that, the value of B is going to be 203.66 millimeters. Multiply that by 2.5, as I said, you will get D to be 509.14 millimeters. At this stage, just leave those two values as is, don't do nothing, and calculate the area of steel directly as rho times B times D, and you'll get an area of steel of 1471.57 millimeter square. Okay. Now, from that, the closest area of steel, or the closest bars that I found, was 3,525, which is giving me an area of steel of 1472.62 millimeters square. You can see these two are very close. Now we need to give some viable dimensions for construction. Obviously, you cannot use 203.66. So usually in our designs we go in multiples of 5 centimeters or 50 millimeters. So in our part of the region we have 150, 200, 253, 350, and go on. As far as the height goes, we start off with 400, 450, 500. So it's only going to be in multiples of 50 millimeters. So now, since I'm using 3,525, I want to know what would be the minimum B that will contain these three bars. So in this case, my B minimum would be 3 times 25, right? Which is the number of bars, plus n minus 1 for spacing, so that's going to be 2. Since my diameter of the bar is equal to 25 millimeters, then I can make the same spacing, which is 25. Again, set dB 25, or for a third of the maximum aggregate in the mix, plus 2 times the cover plus my stirrup 8, If you do that, you're going to get a value of 220 millimeter. Again, multiples of 50, then my B is going to be 250 millimeters. Now to find H, I'm just going to add to D the 25 plus 2, which is 12 and a half, plus 8, instead of plus 40, and that's going to give me an H of 569.64. From that, I'm going to assume H to be 600 millimeters, and my D is equal to 539.5 millimeters. Just to remind you guys, if this is my cross section, these are my 3, 5, 25. Here's my stirrup, which goes around that. Then this D is to the center of those bars. Then I'm going to add this distance right here, which is simply those 3, and that will give me the H. Okay, so now I have a viable cross section. Here is H, which is equal to 600 millimeters. Here is my B, which is equal to 250 millimeters, and here I'm having 3, 5, 25, and the distance D is 539.5 millimeters. So that's my final design. Okay, but I cannot stop here because I need to check if my design is viable or not. Right? Again, this new D is just simply the new H, 600 minus those 3. Okay, so now I have a cross section. Now I'm going to do the check of the solution. First of all, I need to calculate A, and we know that this is simply area of steel times Fy divided by 0.85 F prime C times B. This is now the area of the 3, 5, 25. This is my 420. This is my 22, and then this here is my 250. From that, A is 132.3 millimeters. I will find out C. C is just simply A divided by beta 1, which in my case is 0.85. From that, I'm getting 155.65. Now I want to calculate the net tensile strain, and that's simply D minus C over C times epsilon ultimate. From that, I'm getting that to be 0.0074, and since this is larger than 0.005, then my phi is going to be equal to 0.9. Okay, Rho, I calculated Rho as my actual area of steel divided by B times D, this being for 3, 5, 25, this is being the 539.5 millimeters, and this is being 250. It's larger than Rho minimum. Then I can now calculate M ultimate, and M ultimate I like always to calculate it from this simple formula. M ultimate now would be equal 5.9 times area of steel times Fy times D minus A over 2. Okay, from that I'm getting this to be 263.5 kilonewtons meter, which is larger than 237.94 kilonewtons. So it's about 11% more, close to the economical, because I always like my design to be within the range between, I guess, 0 to 10%. I mean, if it's more than 10% by a little bit, I mean, I guess that's okay. Now, if you're not happy with 11% and you want to do something different, you might say, okay, I'm going to use my B and H that I just found right now and make my area of steel the unknown, okay, and see what type of, or what would be the minimum required area of steel according to the B and H I just found. This is what we're going to do right now. So again, here I'm going to assume that my B is 250, which I found, and I'm going to use my D to be 539.5 millimeters, which is what I found right now. So what I will do here, I will say that my M ultimate, which is usually equal to phi times rho times FYBD square, 1 minus 0.59 Fy F prime C. So I'm going to move this to the other side and say that M ultimate minus this is going to be equal to 0, correct? So now I'm going to put M ultimate down here. I'm going to say that's going to be minus 0.9 by phi. Now rho is the unknown times Fy 420 times B 250 times D 535.5 square. 1 minus 0.59 rho times 420 over 22. Then multiplying and rearranging. So this is the final quadratic equation that I have. Plug that into a calculator and it will give you two values for rho. One is this one and the other one is rho 2. Obviously this is a lot larger than rho max, so definitely I will not use this one, and I will use this rho right here. So you can see that this rho is a little bit less than what we actually found. Okay. So if you don't want to use a calculator and you just want to use equation to find rho, then you can use this equation. It's actually quite handy. Well, if you put in an Excel spreadsheet, it's quite handy. All right. So delta now is going to be 0.59 Fy divided by F prime C. Eta, which is this right here, is going to be phi FYBD square. So if you plug those values in, you will get the same rho value. So as I did that, I found my area of steel to be 1310.04 millimeters square. Again, I arrived at the same conclusion using 3 phi 25. So usually when you have a table of the bars, so if I have this is the phi and then this is the number of bar, I would like to look for a combination where I'm actually getting something close to 310.04 millimeters. But as you can see here, there's really nothing close. The closest one is this one, the 1400, which we already determined. If you go a little bit up, you can see it's might have 2530. It might give you something less, but for regular beams, I'm not comfortable using 530 unless I really have to. 25 is sound about right. If you want to use 22, then this is 1500, which is a lot larger than 1300. So I'm expecting at that point to really have more than 11-12%. You could play with the fact and say, hey, maybe I'm just going to use that and then maybe use a lower H. And again, it's a design. You can't play with it as much as you want. But in this case, you're lowering you're lowering your concrete, but you're increasing the area of steel that you use, meaning you're using more steel for that. So this is what you usually have. Once you get an area of steel, you try and look at the table like this and determine what we usually like, and you will find that when you start talking about crack control. I would like to have more steel bars and smaller diameters, and that will actually help not just in the crack control, it also will help you when you calculate something we call the development length. The less the diameter, usually the less the development length is. But this is something that we'll worry about somewhere down the road. But for now, I would like to find something that's very close to this value right here. And to me, the closest one was 3.525. Here you get in the realm of 6.518. Again, that's a little bit much. In this case, if you want to keep the width of 250 millimeters, then in that case you probably have to use 2 layers. That might actually influence the value of D, and then this might come a little bit tricky. Okay, so again, these are some of the things to think about in your design. So let's move to a different example. In this example, I'm just going to use the raw equation that I found just before. I want to find the area of steel required for the beam below. I'm assuming F prime C 22 megapascal, Fy 420. I'm using phi 8 stirrups. Okay. Here H is given, it's 600 millimeters, and B is given 400 millimeters. I'm giving you the dead load of 11.5 and the live load of 24 kilonewton per meters. Start off like we did with the previous example. we find the ultimate load, and that's going to be 1.2 times dead plus 1.6 times live. It's going to be 52.2 kilonewton per meters. M ultimate now is going to be WL square over 8, and that's going to be 234.9 kilonewton meters. Here I'm calculating rho max, and the reason for that is when I find my rho, I do not want my rho to be larger than rho max. Again, your rho should never be larger than rho. Well, there are instances where it would be, and then that takes us to the realm of doubly reinforced concrete, and that's going to be actually our next recording after that. So here I'm going to assume that I'm phi 25. The only way why I did that is to get a value for D. So from that I found D to be 539.5 square. Again, I calculated delta, I calculated eta, plugged those two into the raw, and from that I got 0.00571, which is obviously less than raw max. Okay, so I'm good. Then the area of steel is going to be 0.00571 times 539.5 times 400, and going to give me an area of steel of 1231.35 millimeters square. Again, going back to that table that I showed you before, so the closest one to me would be 4 phi 20. Okay, now before we finish our solution, which is obviously check, there's another way of doing this, and we call that the iteration method. So I usually don't hold my students to any method. You could either use the way of finding raw, or you could use what we call the iteration method. In the iteration method, what you usually do is you assume some value for A. It doesn't matter, 60, 70, 100, 120. This method actually converges very fast. So in this case, I just took A to be 60. Here I'm going to cheat a little bit because I already determined that I'm going to use 4 phi 20. Then for that I'm going to use calculate D based off of that, and it's going to be 600 minus 40 minus 8 minus 10, and so for that I'm having 542 millimeters. Okay, so now I'm going to use two equations for the iteration method. The first equation that I'm going to use the moment equation, and that is simply 0.9 times area of steel Fy times D minus A over 2. Okay. From that, the only unknown now is going to be the area of steel. So now the area of steel is going to be the M ultimate divided by 0.9 phi, 420. This is the calculated D minus the assumed A, which is 60 over 2. So this is giving me 1213.73 millimeters square. All right. Now I want to check if the A that I chose is correct or not, and from that I tap into the second equation, which is simply the compression is equal to tension. From that now the tension is again area of steel, which I just found, times Fy. The compression is 0.85 F prime C A phi B, so from that A is my unknown and B is 400. So I'm getting now A to be 64.9 millimeters. Now, if it were me, usually if I within 10, 15 millimeters, I would just stop right there and say, hey, I'm happy with the A that I assumed, and then just go with this area of steel right there. If you are far off, then you do a second iteration. I'm just doing that here just to show you how to do the second iteration. So what you would do now is you would take this new A that you found and then re-plug that into the equation of area steel. Okay, so from that you will get a new area of steel value, which in this case was actually 1219.57 millimeter. As you can see, the difference is very small, and then you go back and calculate A from here, and the value of A is 65.21 millimeters, which is very close to 64. So again, I will just go with 1219.57 millimeters. Going back to that table, I'm going to use now 4 phi 20, so it's the same conclusion. So if you don't like to use the direct equation for raw, use the method of iteration. Both of them works and both of them are fine. So to conclude my solution, I'm going to now check the solution for myself. Now here, this is the area of 4520, which is 1256.64. You can see how close that is to the found area of steel, times Fy divided by 0.85 times 22 times 400. This is 70.56 millimeters. Again, this is different than the assumed, but it has no relation to the assumption because, again, now I'm using the actual area of steel that I found. For that, now C is going to be A over beta 1, and from that I got C to be 83.01. Now the net tensile steel is going to be epsilon ultimate times D minus C over C, and that's much larger than 0.25. Just check for raw, it's more than raw minimum. Then I'm golden. From that, now M ultimate is 0.9 times area of steel times Fy times 442 minus A over 2, and M ultimate is 247.7, bigger than M ultimate, which is actually very close to it. I think this is probably in the realm of 2%, so this design is actually pretty, I would say, economical, if you will. All right. So that actually ends the part of the examples for this series. As you can see, usually design is, you have the design part. Once you finish with the design, you go to the analysis part, okay? Because you need to make sure that your solution is safe, economical, and viable. So you guys stay safe out there. Have a nice day, and see you soon.